Hello, everybody. Welcome to this session, this continued expert talk series, basically. Welcome, everybody, for joining us on this discussion on water chemistry. I'm your host, Anand Karayalkar. I'm the technical specialist at Forbes Marshall R&D, responsible for new product development. And I also lead the Thermodynamics Connect initiative for Forbes Marshall, specifically with the industry academia collaborations across the world. And we have with us Aditya today, one of my earliest connects with Forbes Marshall, if I remember correctly. One of the first products I actually worked with in Forbes Marshall is in collaboration with Aditya. He's the principal lead for integrated solution systems at Forbes Marshall. And brings with him a wide range of expertise, not only in terms of product development, like I said, which we did together, and subsequently, and also the area of water chemistry specifically, which is a crucial element for water and steam circuits everywhere. Welcome, Aditya.
Yeah, thanks, Anand, for actually inviting me on this wonderful platform to discuss a most interesting subject in my life. I would say. Thanks for it, and let's begin interaction on this.
Thank you. So one of the first things, we often discuss steam engineering concepts. The platform is actually used for sharing our experience, our expertise, and also the ground reality of what industry looks for in terms of technology, so which benefits the students, the academic communities, but also to other industry participants who may benefit from gaining the knowledge that comes out of these interactions. So we've had discussions on steam use in process industry, for example, the ubiquity of it all. Okay. But one of the things that has kind of seemed missing is the link between academia and industry in terms of where steam is relevant. Okay. And the reason I wanted to target today's session specifically on water chemistry is because it actually opens a new avenue of understanding how steam is used in industry, but for an area which is already prevalent in academia. So, for example, almost all the mechanical engineers in the audience would know that we are taught Rankine cycles, we are taught steam cycles, boiler, turbine, condenser, pump, that kind of loop. Okay. But what happens in the background is also that much important, particularly in practical situations. So my first question to you would be, if we are looking at steam use in power generation specifically, not process heating, which is a separate discussion, but power generation specifically, can you give us some insight in terms of how that looks like from a fundamental concept, which we learn in classrooms, to what it looks like in an industrial setting, which is considerably more complex?
Yeah. So as you are talking about Rankine cycle, and I believe Rankine cycle was developed or study was made on a steam properties way back in 19th century. By various professors, various scientists in Europe, including William Rankine, who is Scottish professor, and he worked a lot on actually properties of physical properties of, I would say, steam and how their behavior at various pressure and temperature. And that's why this Rankine cycle evolved. And I would say it's as old as 200 years. So last 200 years, whoever has done mechanical engineering has studied this cycle in their textbook some or other way.
Yeah.
So talking about Rankine cycle, actually it is a closed cycle, as everyone knows.
Right.
And it has four basic processes. First is a constant pressure heat addition, which takes place in the steam generation. Okay,
that's a boiler.
Yeah, that's a boiler itself. I would not say boiler always, because you go to nuclear power plant, you go to geothermal power plant, you go to solar thermal power plant. Anyway, you can add heat in water and convert it into steam. So I would say it's a process and which is adapted quite well in an industry by various ways, including waste heat recoveries also.
Right.
Then once steam is made, then it is used on a steam turbine or steam engine where the work output is taken out.
Right.
And this is adiabatic expansion where we assume that there is no heat loss through engines and steam turbine casing, and we expand the steam and take out the work, which generally used in a power plant to generate electricity by coupling it to generators through gearboxes.
Yeah.
And then as everyone in thermodynamics knows, there is a heat source which we already talked about as the boiler or steam generator, and there must be some heat sink where you need to reject heat back to atmosphere, and which is done in a condensers.
Yes.
The condensers also got evolved over years. It's a water-cooled condensers. Now people are talking about air-cooled condensers, looking at huge water utility required for cooling.
Correct.
So that's a third equipment, I would say, in this cycle. And last, once condensate is recovered back, we pump it back in a boiler to increase its pressure to boiler pressure. So all these four processes, I would say people are studying them for last 200 years. So it's as good as saying that there is a huge mind and brain went into development and optimizing this cycle over the years. Talking about Rankine cycle, there was a lot of additional equipments were added later on, like superheaters, reheaters, there were a lot of efforts made how we can increase thermal efficiency of this particular cycle by increasing pressure of boiler, at the same time by reducing pressure in a condensing area. So by increasing area within curve, we try to increase its thermal efficiency by adding different means. So over the years, it developed a lot, and it is implemented everywhere in thermal power plants. So as I said, it's not only for some fossil fuel-based thermal power plant, it's also adapted to nuclear thermal power plant and also to solar thermal and geothermal, which is, you can say, renewable energy sector. So this whole cycle is quite mature, and there is a lot of opportunity to still optimize it as metallurgy is evolving, so boiler pressures are increasing. So people used to talk about subcritical boiler, then they go into supercritical power boilers, ultra supercritical, and now we are talking about advanced ultra supercritical power boilers for our Indian market. So it's very, very interesting field or subject where thermodynamics physics is actually, playing a role in a real life scenario.
Yeah. Actually, so I find it very interesting. I mean, you have spent a lot of time interacting with these systems in real time. But also the first thing that you try to explain is again going back to the thermodynamic principle, where we are talking about the second law of thermodynamics, that if you have a heat source for a cyclic system, you have to have a heat sink. Correct. Yeah. And that's where the condenser comes in. Yeah. That's very interesting. The second thing I liked about your comment was on the thermal efficiency, how you can improve that. Yeah. Now, we know that if we look at the fundamentals of thermodynamics, if you look at even the benchmark efficiency of Carnot cycle, the IDN cycle, it talks about increasing the heat addition temperature and reducing the heat rejection temperature to improve efficiency. Yeah. And both the examples that you gave, that if you increase boiler pressure, you can get it to higher and higher temperatures. And also at the same time, if you reduce the condensation pressure, you can reduce the condensation temperature, which is exactly what we are trying to do in terms of approaching that threshold. Correct. And that way, the modern Rankine cycles are very much mature, what you mentioned. I mean, that's also quite interesting, that it's almost at the pinnacle of technology, with the exception of metallurgy. So right now, the limits that the current cycle has is on metallurgical side.
So that actually, when you talk about metallurgy, even I would say there is no limitation on that also. Metallurgies are also quite well evolved.
Right.
But whenever you want to implement any technology in an industry, money comes into picture. So cost of those materials, cost of per megawatt generation of power is going to matter, because we all pay electricity cost and we want to be free electricity everywhere. So that is actually real challenge. To increase efficiency, you need to invest in a materials or in a capital equipment. And that is going to be, not only technical choice, but also becomes slightly commercial decision when it comes to implementing new technologies in industry.
Yeah. That's a very good point, actually, because if we are even looking at, one of the hopes I have for continuing this series, and we will conduct a few more sessions as we go along over the year, But one of the hopes I have for this particular series is to actually bridge the gap between industry and academia, so that even academia finds relevant topics which are important to industry. So that's a very interesting comment that you made. So even though the existing technology may be there, the commercials will always be an important aspect of it. Yeah.
Correct.
This is also a challenge in terms of adoption of renewables. Okay. So in terms of renewable adoption in the world, most of the industries want to do this, but where the commercial don't really make sense, it becomes a real challenge, even though they have good intent of doing it. So that's definitely a challenge.